Welcome to this explainer. Today, we are going to act as game designers to decode the exact strategies you need to master your Cambridge physics exams. Specifically, we're focusing on syllabus codes 0625, 0651, 0652, 5054, and even setting the foundation for 9702. And we are zeroing in on one of the most challenging boss fights for students: complex motion graphs. Now, I want you to think of your physics exam not as some terrifying, insurmountable hurdle, but as a system with very distinct rules. If you know the rules, you can absolutely win the game. Every year, we see two types of students totally wipe out on these questions. Let's call them Alex and Sam. Alex is the kind of student who overloads every answer with raw, unfiltered physics facts, but provides zero actual analysis. And then you have Sam. Sam rushes through the paper, completely misses the command word requirements, and loses easy marks. We are going to fix both of those errors today. Our source material lays out an incredible application-first approach to cracking these motion graph questions, and we've built a structure that will act as your ultimate cheat sheet to boost your mark potential from 0 to 100%. So grab your notebooks, get focused, and let's dive right into this.
Okay, let's take a quick look at our structured roadmap for leveling up your exam answers today. We are going to hit 5 key stages. First, the motion graph challenge. Second, the 4-step strategy. Third, real-world physics applications. Fourth, the examiner's lens. And finally, we will master the memory prompts. Let's jump into Section 1.
Section 1, the motion graph challenge. We are starting right away with the ultimate trap that students like Alex and Sam fall into. And honestly, you've probably been there too. It's rote memorization without actual physical understanding. It is like trying to beat a video game by just memorizing the controller buttons without ever actually looking at the screen. You memorize a textbook definition, right? But the moment the exam throws a slightly unfamiliar complex graph at you, all that memorized wording suddenly feels completely useless. You panic, you write down a random formula, and the examiner immediately reaches for the red pen. We need to completely rewire how you look at these graphs, so you can start racking up those green check marks instead. To avoid getting stuck in that memorization trap, our application-first teaching method demands a totally different mindset. Before you ever write down form a vocabulary, and definitely before you start blindly throwing equations like V equals U plus AT onto the page, you must stop and ask yourself this critical fundamental question: what physical effect, measurement, or prediction actually depends on understanding this graph? You have to make the idea feel necessary. It's not just a decorative line on a grid, it represents a real physical event happening in the universe. Once you understand the why behind the graph, the physics vocabulary just naturally follows. This concept brilliantly illustrates the difference between an overloaded, rote-memorized answer that earns 0 marks and a strategic, flawless answer that explains the actual physical effect. Think about the flawed approach for a second. It's heavily dependent on memorized buzzwords, and it completely falls apart if the question's context shifts even slightly. The examiner reads it and immediately knows you don't really get it. Now compare that to a top-tier, high-scoring answer where the student actually reasons their way through the physical cause and effect. They aren't just reciting words like a robot. They're explaining reality. They're hitting those assessment objectives perfectly. Moving on to Section 2, the 4-step strategy. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, so let's move to the specific strategy that acts as your structural cheat code for answering these complex questions. Top students use a framework, often called PEAL, point, evidence, explanation, link. We are going to apply that directly to physics. So the crucial point here is to strictly follow these 4 linked steps, which perfectly parallel the absolute best structuring frameworks for Cambridge physics exams. Step 1, identify the quantity or phenomenon. This is your point. What are we actually looking at? Step 2, state the relationship involved. This is your evidence. How do the variables interact? Step 3, explain the underlying physics. Why is this happening? And step 4, connect it to an observation or real device. This is your link. Let's say you're looking at a velocity time graph of a skydiver. Step 1, the phenomenon is terminal velocity. Step 2, the relationship is that acceleration decreases as velocity increases until acceleration is 0. Step 3, the underlying physics is that air resistance increases until it perfectly balances the downward force of gravity, making the resultant force 0. And step 4, the observation is the skydiver falling at a constant maximum speed. If you strictly follow this chain, you literally force the examiner to give you full marks. Now, a massive part of executing those 4 steps successfully relies on exactly how you build your explanation. A huge mistake is jumping straight into complex math or physics jargon before you've established the reality of the situation. By starting your thought process with a concrete example in everyday, straightforward language, you build a solid, logical foundation. You might start by just thinking, okay, the object is getting faster. From there, you can safely bridge the gap to precise symbolic physics vocabulary, only when your fundamental logic is sound. So getting faster safely translates to velocity increases, which then translates to positive acceleration. It is a gradual, deliberate translation from what you see with your eyes to the specific physics terms the examiner is hunting for on the page. And this exact logic applies directly to motion graphs. When you are interpreting graphs in your exam under the pressure of the clock, you must explicitly stress what the features of the graph mean physically, rather than just describing geometry. The examiner does not care if you know that the line curves upwards. You have to extract the physics. What does the slope mean? Well, if it's a distance time graph, the slope is speed. If it's a velocity time graph, the slope is acceleration. What about the area under the curve? On a velocity time graph, that area literally represents the physical distance the object has traveled. What about direction or the specific shape of a curve? You have to consistently link the visual feature you are seeing to its hard physical meaning. That is how you decode the data. Section 3. Real-world physics applications. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's step out of the classroom for a moment to see how these theories actually govern our reality. You see, the ideas we extract from motion graphs appear absolutely everywhere in the real world. They are foundational in heavy engineering and designing safety mechanisms in public transport, energy systems, and even bleeding-edge medical technology and astronomy. For your exam, especially in those longer, structured questions, you must always be able to name at least one real-world situation where the motion graph concept actually matters. Take car safety mechanisms, for example. Understanding how to extend the time of a crash, which you can model on a motion graph, directly explains how crumple zones reduce the force on the passengers. But remember, don't just name the application. You have to explain why the physics helps us actually predict or improve outcomes in that specific situation. And what's really interesting here is that this provides the absolute golden rule for tackling any Cambridge exam question. Insist on cause and effect rather than isolated facts. If you were to do a 60-second data scan challenge right now on a complex physics chart, the core trend you need to extract is always cause and effect. And this doesn't just apply to motion graphs. Whether you are tackling questions about magnetic fields, particle physics, electrical circuits, or wave behaviors, this is your guiding light. The examiner wants to see that you deeply understand how one physical action directly triggers another, not just that you can spit out a random list of memorized trivia. If voltage increases, what physically happens to the current and why? Causing an effect. Section 4. The examiner's lens. It is time to look at your answers exactly how the Cambridge examiner will see them. We need to figure out exactly what sentences are losing you marks and what structural methods guarantee that you get those marks back. Notice how incredibly easy it is to fall into common exam weaknesses. Things like just writing down a formula, say V = d/t, but completely failing to define the variables or the context. Or quoting a process without providing the physical link, or throwing out an example without showing why it logically follows from the physics. These are all classic flaws that cost students dearly, but you can completely eliminate these errors by utilizing the safest, most bulletproof method available. First, start with a clear definition. Second, state the relationship. Third, provide the deep physical explanation. And fourth, show the real-world application. This is your ultimate defensive strategy when you are sitting in that exam hall. Finally, Section 5. Master the memory prompts. Let's review the prompt system designed to firmly lock these concepts into your memory for exam day. Because having a strategy is fantastic, but you need a reliable way to instantly recall it when the clock is ticking down. So, here is your ultimate revision toolkit. When you are studying any motion graph topic, I want you to test yourself with a 30-second speed writing challenge using these 4 prompts. Prompt 1, what is the core idea? Prompt 2, what changes physically? Prompt 3, what quantity or specific graph shows it? And prompt 4, where is it used? For example, if the topic is deceleration, the core idea is slowing down. What changes physically? Velocity decreases over time. What graph shows it? A velocity time graph with a negative slope. Where is it used? A train applying its brakes as it enters a station. If you can confidently answer these 4 revision prompts aloud for every syllabus point, you can confidently tackle literally any short answer or structured question on the 0625 paper.
So I leave you with this ultimate challenge to test your true understanding before you sit down for your Cambridge exam. Can you explain the physics behind a complex motion graph using a clear cause and effect chain right now? Remember the 3 rules that guarantee top marks. Decode the command words, apply your framework step by step, and manage your time matrix. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this explainer with a study partner. Ace the Exams. Your Cambridge success starts here.